in the IJCAI trustee, and I was the past president of IJCAI. Today, we are very happy to have Daniela Rus to give us the John McCarthy Award talk. To start with, let me say that the IJCAI John McCarthy Award is intended to recognize established mid-career researchers, typically between 15 and 25 years after obtaining their PhD, that have built up a major track record of research excellence in AI. Nominees of the award will have made significant contributions to the research agenda in their area and will have a first-rate profile of influential research results. And so this year's award is awarded to Daniela Rus, who is the Andrew and Erna Viterbi Professor of Electrical Engineering and Computer Science and Director of Computer Science and AI Laboratory, CISO, at MIT. Rus's research interests are in robotics, mobile computing, and data science. And she is a class of 2002 MacArthur Fellow, a Fellow of ACM, AAAI, and IEEE, and a member of the National Academy of Engineering and the American Academy of Arts and Science. She earned her PhD from Cornell University. So without much ado, let's welcome Daniela to give the talk.
Thank you so very much. I am so honored to be acknowledged with the IJCAI John McCarthy Award, and also to be here with all of you today, even if it's over Zoom. And I would like to remark that some of the most important ideas about the past, present, and future of artificial intelligence are due to John McCarthy. So from my point of view, we can't really understand AI and John McCarthy's role in shaping AI unless we know a little bit about where it came from. So just picture this. It is 1956. The world looks a lot different than today, especially in technology. And a young John McCarthy, who you see on the right in the back in this photo, along with his friend Marvin Minsky in the back in the middle, decide to gather their friends, and they go off to the woods of New Hampshire, where they spend time talking, hiking, and no doubt enjoying some good food and wine. And when they emerge from the woods, they announce to the world that they coined a new academic field of study called artificial intelligence, which includes the science and engineering of machines that exhibit human-level intelligence in how they move, how they speak, how they see, how they reason, how they play games, and even how they learn. So these founders of AI believed that one day machines will be able to exhibit human-like intelligence. And since then, the AI community has focused on pursuing these goals, making numerous contributions to machine vision, to machine learning systems, to robot systems, and so many more. So this 1956 Dartmouth meeting, co-organized by John McCarthy, is truly a watershed moment in computer science. Now, I'd like to remark that at that time, computers were so large and expensive and hard to access, so that a person needed a lot of expertise in order to know what to do with them. But all of that changed with a smartphone. The smartphone truly democratized computation because suddenly there is an application, there is an app for every task. And in fact, computing has become so normal for us that we don't even notice how central it is to almost every aspect of our lives. And today, I would say that we are about to experience this type of change again. But this time, it is AI that is transforming how we live and how we work by introducing machines that help people with cognitive and physical tasks. And John McCarthy has made a lot of contributions and has done a lot to imagine this kind of future. And this was more than 50 years ago. And so, for instance, in 1950, John McCarthy authored a paper called Programs with Common Sense. And this program, this paper has laid out the principles of his programming philosophy and described a system which is to evolve intelligence of human order. Now, John McCarthy has been visionary in many other ways. For instance, in the 60s, he hosted a series of simultaneous computer chess games carried out via telegraph against rivals in Russia. And these games lasted 9 months between 1966 and 1967. And I see these activities as developing a kind of infrastructure and thought leadership for our broad interest in demonstrating how AI can be a partner for people in complex games. Now, the paper that has been most influential on me has been one called Computer-Controlled Cars. In this paper, John McCarthy imagined the future of self-driving cars. And this is what I'd like to talk about today. Now, many of the technical challenges identified by John McCarthy remain current today. For example, his work on Lisp machines and on time-sharing computing has been the precursor of modern programming languages and on cloud computing. And the ideas behind programs with common sense and computer-controlled cars inspired me, and I am deeply grateful for this. Now, today, many people fear a potential future with robots and AI machines. But what I say is that instead of fearing robots, we should ask ourselves, how much work could we offload to machines? Because this will increase the quality of our lives. And so, for example, autonomous cars, autonomous wheelchairs, scooters, golf carts, city cars, will give our parents and grandparents a higher quality of life in their retirement, with personal mobility available anywhere, anytime. The same technology for autonomous driving that John McCarthy imagined more than 50 years ago can be used for food deliveries, for logistics, for stocking and restocking products, for cleaning. There are so many possibilities. I would say that today, robots have already become our partners in industrial and domestic settings. They mow our lawns, they vacuum our floors, and they even milk our cows. And in the future, they will do so much more for us. And one area of focus about a future with better living and better machines is in the area of transportation. So, as we think about autonomous driving, I would like to identify that there are several key parameters that emerge as we think about capabilities and possibilities in this space. For instance, how complex is the environment where the car is moving? How complex are the interactions between the car and the environment? And how complex is the reasoning of the car? Now, we have deployed solutions for a number of years that live towards the origin of the system of coordinates defined by these features. And in particular, here you see an example from a deployment from 2014 from my group. And this is because we've had vehicles that move slowly in low complexity environments, and they exist. And they're safe. They're safe because the uncertainty is low and the vehicle has time to process the events. However, it's important to realize that the sensors used by autonomous vehicles do not work in weather. And because the uncertainty of the perception increases significantly if it rains hard or if it snows. That's why most autonomous driving companies are testing their vehicles in Arizona, where it never rains nor snow. And the uncertainty of the vehicle prior for decision-making also increases in the case of extreme congestion with vehicles, with people with scooters. And if you look carefully on the right, even with cows, which you can see in this video I took from the back of my taxi some time back when I visited Bangalore. So the point is that there are many preconditions and many that revolve around uncertainty in perception, planning, learning, and reasoning before we can get to the broad goal of robotaxi. And so today I'd like to actually tell you what some of my, my group's advancements towards this direction are. And before we look at that, I would just like to start by showing you what is the autonomy recipe. Say you have a car or you have any other vehicle on wheels. What can you do to turn it into an autonomous machine? Well, here's how it works. You start with a car. This is the robot platform. You add to this platform sensing. And for autonomous driving, laser scanning and cameras are the two typical sensors that we add. These sensors are used to create maps and to detect obstacles. And they do so by aggregating laser scans of the world. And then this data is used to help the vehicle go from point A to point B, but also it helps the vehicle estimate where it is in the environment because the vehicle now can take a scan and look at its surrounding environment as compared to what there is in the map. And that's the localization problem. So once the vehicle can localize, it can plan a path from the current location to the destination, and then it executes the path, but the execution has to take into account any kind of dynamic obstacles that the vehicle might encounter. So that's basically the autonomy recipe that is used by most autonomous driving solutions today. Now, what I'd like to do is examine how can we enable self-driving vehicles to operate in more complex environments. How can we incorporate risk in the control loop of these systems? How can we handle congestion and interactions with human drivers? Because answering these questions will get us further out in our system of coordinates for safe autonomous navigation. So now, if we take a step back and we look at a traditional AV pipeline, we start with sensor fusion to talk about what is happening around the vehicle. We detect obstacles, we localize, we plan, and we act. And what's interesting about this pipeline is that, in fact, many of the algorithms that are used in each of these modules has to be fine-tuned for every type of environment the vehicle is in. So if it's nighttime driving, if you're on a road without markings, if you're in rainy weather, if you're in the city or in the desert or in the woods, all of these types of environments require special features. And so we had the idea that instead of creating this long pipeline with modules that have to be customized in so many different ways, we had the idea that maybe we can learn directly from people how to drive. We can learn by watching humans how to drive. And the idea here is to connect directly the data from the sensors to the actuation system through a machine learning algorithm. And we call this end-to-end learning because we aim to optimize a single learning algorithm which directly takes us from raw sensory data all the way to control signals like steering, the wheel, and the accelerator. Now, we can learn a model to go from raw perception, and you can think about raw perception as pixels from a camera, and a noisy street view map. So this is not the high definition maps that are created with laser scanners and used by traditional autonomy solutions. So we can learn a model that can go from raw perception all the way to steering. And in this case, what we do is we directly infer a full continuous probability distribution over the space of all control signals. You can see some red lines that indicate the inferred trajectories of the vehicle projected into the image frame, and the opacity represents the learned density function by our model. And we can do this by training a deep learning model to output the parameters of this conditional distribution directly from human driving data by observing humans how to drive. So we provide as input direct feedback from the camera and the course topological map. And what we get is a model that gives us the likelihood over the control space of all control. And then we can provide an optional output trajectory if we want to direct the vehicle to a specified location. So interestingly, this method that allows us to go from directly observing humans, in other words, taking human data to learn this model, it turns out that the model can learn to generalize to new road types that were not part of the data set. For instance, in this example, we placed our vehicle in a situation that requires a roundabout. There was no example of roundabout in our data set, and yet the vehicle was able to learn how to and to execute a correct route around this roundabout. Now, in some cases, when we think about navigation, we come across images that are very tricky to understand. So if you look at this picture, I would say that this is a very tricky picture to analyze. We have an intersection coming up, but what type of intersection is it? How can we handle this? Well, it turns out that if you squint and you look carefully at the map, you see that there is a stop sign, there is a zebra crossing. So maybe you have a cross intersection, but you have to look very carefully at the image in order to figure this out. With our algorithm, the network is also able to identify the kind of road situation we are in and correctly predict the true map and the location of the vehicle within this map. And so this approach to representing continuous distributions is also helping us with localization and with handling complex road situations like the one you see in this picture. So we have developed the system, we have implemented it on our vehicle, which happens to be a Toyota Prius, expanded with sensors and computation like I showed you in the autonomy recipe. And so here's the vehicle driving for the first time in a road situation it had never seen before. This vehicle was trained in urban settings in Cambridge around MIT, and now it's driving in a rather rural wooded area where the roads do not have markings. And yet this vehicle is able to follow the road and also to arrive at the correct location. The vehicle is able to cross through intersections and navigate to the destination. Now, if we look a little bit inside the computational engine that's driving this vehicle, you can see what goes on in this picture. So what you see here is, let's see, on the left, on the lower left, you see the course map, and you see in red where the vehicle is on the map. What you see on the top left is the camera input stream. On the bottom left, you see the attention map. That means where in the image the network is looking. And then you see some small boxes. Those boxes show you what happens in the convolutional layers that are used to understand the perception of the vehicle. And here in the middle, the box that has the yellow, blue, and green dots is the network that is driving the decision-making of this vehicle. This network has over 100,000 neurons and over 500 million parameters. And if you look at the attention map of this network, it's kind of all over the place, but nevertheless, the vehicle is able to drive down the road. The point is that we see correct behavior, but we don't actually understand what happens inside the brain of this system. So in order to get a better understanding, we had the idea to change the model of the neuron. So the neurons used in classical deep network architectures compute a very simple function. It's a thresholding or a step function. And then they result in very large architectures with many nodes in the hundreds of thousands of nodes space. We took inspiration from the poor earthworm, whose neural circuit has been fully mapped. Turns out the earthworm has about 300 neurons, and biologists have figured out the chemistry of each neuron, and they have figured out that the neurons are a little bit specialized, and each neuron computes a differential equation. So it's more complex than doing a simple step function. But we took this idea and we adopted it to our driving scenario. And we designed what we call neural circuit policies, where now each neuron is more powerful. It computes a differential equation instead of a step function. And with this new model for the neural control of a self-driving vehicle, we can achieve the same performance as in the previous case with 19 nodes. You can see the 19 nodes in the middle of the slide. And the left-hand side with the small boxes remains the same because that's the part that processes the image. The part that makes decisions about what to do is now 19 nodes rather than over 100,000 nodes. And notice that the attention map of this solution is much cleaner. The network looks on the horizon and on the side of the road, which is much more consistent with what people do. So we're very excited about the possibility of getting more insight into what neural networks do by using this kind of method, by using what we call neural circuit policies, where now neurons are much more powerful than in the classical model. Now, the thing is that the state of the art of end-to-end perception to control learning has some limitations. And the limitations rely on collecting the gold standard of human driving data sets. And training the model is limited by this because you can't imagine generating real-time crash situations to train the vehicle. So how to enrich the data that is used to train self-driving vehicles? Well, one idea is to enrich and augment our models by using simulation. What we have done was to develop a high-fidelity simulation engine where we compute one high-fidelity trajectory from a real driving scenario, from a human driving data set. And then we make a lot of variation scenario by sampling trajectories within a simulation space. So here's how it works. We start with a photorealistic data-driven simulation engine, and then we generate new control trajectories, and we end up with real-world transferable reinforcement learning, which is end-to-end learning without human imitation. And so here's what it looks like. So on the left, you see the true data set that was collected from a human. And on the right, you see what we can do in simulation by generating from the true data set, generating a lot of erratic driving, a lot of the kind of driving that is hard to generate for real. And with this approach, it turns out that we can have direct deployment onto vehicles, and we have superior robustness to recovering from challenging orientations. In other words, in our experiments, we have tried orientations where the car was pointed off-road, even sideways, and our system was able to recover from all of these situations. So I think it's really exciting because we are at the point in time where we can imagine machine learning systems that directly learn from humans how to drive, that can augment the human data with a great richness of data to capture dangerous and corner case scenarios. And we can do so in compact neural networks that include a small number of nodes that can actually be inspected and audited. So that's a significant step towards creating systems that are more adaptive and more able to deal with complex scenarios. But some of the complex scenarios involve very crowded environments like the one you saw in Bangalore or the one you see in this picture. And with the current methods, where one of the steps is to identify and label all the obstacles in the environment, we actually have issues because machine vision algorithms make mistakes. They have trouble identifying, say, people when the people are dragging or pulling things. And these high-end tables are often identified as people. And so we wanted to further simplify and create a solution that is agnostic to static and dynamic obstacles in the environment, but also able to compute a dynamic risk without explicitly identifying the obstacles. And the way we do that is by defining a safety net around the vehicles. We call this safety net a risk level set, depending on your level of risk or your tolerance to risk. These sets are bigger or smaller. And then we can develop a definition of a clutter as a metric to quickly assess safe regions. And we can develop control algorithms that are able to adapt to different types of clutter and that have risk as a tunable parameter in the planning. And this gives us a minimum information system that does not need to require a lot of knowledge about what the agents in the world are doing. So in other words, we define a cost function, and we develop a controller that is based on this cost function. And the agents now are no longer represented with what they are, but with these bubbles that define their associated risk. So there is some math that shows you how to set up these risk level sets. And this idea can be implemented directly on systems of autonomous vehicles, and they can be implemented to represent different levels of risk. This is an example where we have tuned the risk parameter to denote conservative driving, and you can see the blue car has gone in the middle and sort of is not moving because it has such a low tolerance to risk that the world is mostly gray around it. But in this case, we have a more aggressive driver, and so an aggressive driver has to cope with lower risk regions, and now there's much more white space where this controller can maneuver. And we can do this for a variety of road systems for multiple vehicles at the same time. So this is really exciting because it can be applied to road situations, but also it can be applied to pedestrian situations and other human-centered environments. In this case, you can see in white the free space, and in gray where the robot cannot go. And this example was or this experiment was done without any knowledge of what the people in the space would be doing. And it's really wonderful to see the ability of this much simpler approach to driving being carried out. So I'd like to tell you about one more feature of autonomous driving, of our efforts to increase the capability of autonomous driving systems. And this is in spaces where humans and robot cars coexist. And in fact, the issue is that human drivers and robot car drivers do not understand each other yet. Because robot cars get confused when executing maneuvers that require coordination, as they don't really understand if the human is yielding or not. And so more specifically, robot cars have trouble deciding whether to speed up or slow down when they have to do unprotected left turns. In the situation of an aggressive egotistic driver, that's accelerating, the robot should slow down to let the vehicle go. But when the driver is not more generous and slows down to let the robot go, then the robot should seize the moment and go. So we set out to understand how to solve this problem. And what we ended up doing was to create a model for the behavior of the other agents surrounding the ego car using one parameter from the social psychology literature called social value orientation. And this parameter has been studied by this community and is an angle that measures rewards to self versus rewards to others. It's a mathematical parameter that can be incorporated in a learning function or in an optimization function. And so there are many personalities that can be described by this angle. Most relevant for us are the pro-social, altruistic, and egotistic behaviors. And here's how you can understand the SVO. Let's say you have to split $100 with a stranger. Well, you can keep $0, give it all away. That means you're altruistic, and this corresponds to an angle of 90 degrees. You can split 50-50, then you're pro-social, and the angle is 45 degrees. Or you can keep everything, and that means you're egotistic, and the parameter is 0 degrees. So it turns out that in human-robot car interactions, we can observe the interactions and we can figure out what is this parameter. We can measure reward to self versus reward to others. And we can begin to model what the correct response is. So if you have a better prior for the road situation, and in other words, if you observe a car and you understand that it's going to be an egotistic car and you want to do a left-hand turn, then you slow down. But if you can assess that the incoming car is altruistic, then you should speed up and go. So you can choose one controller versus the other depending on this increased situation awareness. So there is a lot of math to actually model correctly what happens between the vehicles on the road. And in fact, our solution has 3 steps. The first step is to estimate the social value orientation. And the second step is to set up a response game where each agent, in other words, each car on the road, maximizes its individual utility. And the third step is to do inverse reinforcement learning and to calibrate the rewards using real data sets, like, for instance, the NGSIM data set. Let's see, I'm just watching the time. We can set up a policy, a utility minimizing policy that, and in a traditional setup, you have an individual reward and you can compute the utility over the time horizon, and you compute the best control that maximizes the utility, let's say the yellow path. But by having better situation awareness about the world, you can choose one of the other paths. So for instance, by setting up a joint reward that is weighted by the SVO, you can measure the utility over the time horizon, and you can find a controller that maximizes the utility, but as parameterized by the personality of the vehicles that you see in your surrounding. So going one way if you have altruistic, or another way if you have egotistic behaviors. And so here's an example where the AV is in red and the pink vehicle is altruistic. The AV has the ability to adapt and apply a more aggressive controller to speed up in front of the altruistic vehicle. On the other hand, here the AV is faced with an egotistic driver. The pink car is egotistic. Therefore, the AV has to slow down. Now, you might even have pro-social drivers who get out of the way in order to create gaps for the AV to merge. With this approach, with the ability to measure the personality of the other agents around the ego vehicle, we get better situation awareness, and we are able to respond much more correctly and effectively because the situation awareness is better. So here I just wanted to show you an example that gives you a sample data set from the NGSIM data set, and you can see two cars, one in green, one in purple, and you can see how the cars estimate the SVO in real time. And well, it turns out that using the same NGSIM data set, we can show that estimating the driver SVO improves trajectory predictions by 25%, and this in turn increases the traffic flow and safety. With this, I think I've reached the end of my my time allocation, and I want to conclude by reminding you that autonomous driving and in general autonomy depends critically on the uncertainty in data, in sensors, in models, in control. And there are so many sources of uncertainty in safety critical autonomy, like on the roads, but also in the air, or in robots that manipulate things in manufacturing. And measuring this uncertainty and finding ways to mitigate and reduce this uncertainty is critical to making systems that will be increasingly more capable for the future. I have told you about a particular technique called neural circuit policies that aims to reduce model uncertainty and auditing by replacing the model we use for the neuron from the step function to a differential equation. I have also told you about risk level sets for simplifying the object recognition aspect of autonomous driving, and risk level sets are also able to reduce risk and to adapt to more risk averse or risk prone situation. And finally, I have talked to you about a new approach to identifying the personality of the other agents around the ego agent, the ego vehicle. And this is called the SVO, the social value orientation. The SVO, I believe, is a great step towards enabling humans and robots to interact together and to adapt to one another. And with these technologies, I would say that today we have an extraordinary landscape of autonomy where we have a lot of readily deployable products, but at low speed in low complexity environments. Tomorrow, in the near future, we will see increased speed and complexity, and we will see mixed human-driven and robot-driven roads using some of the techniques I have alluded to in this talk. And for the future, I would love to have pervasive self-driving flying cars because ultimately when I'm stuck in traffic and I'm worried about being late, what I want is to go up in the third dimension and go directly to my destination. And so with this, I will stop and see if you have any questions.
Thank you, Daniela. So we actually have a mechanism to ask questions and for Daniela to pick the questions in the Q&A part. So people who have questions, please use the chat function to leave questions in Q&A. And Daniela, you can look up there there's one question now.
Yeah, so Maria asks about the roundabout example, and she asks whether the car learns rules for yielding right of way or otherwise handle other traffic. And so, yeah, the car learns how to follow the curvature of the road. And by combining following the curvature of the road with a desired topological path to the destination, the car will follow that path. I guess the car is not yet ready to do the extensive interactions that you might find maybe if you try to go around the roundabout in Paris at Arc de Triomphe, where you have hundreds of cars spinning at the same time and 6-7 lanes of traffic. That is the kind of high speed and high complexity of interaction scenario I alluded to. And I said that today's vehicles are not ready to cope with those types of road scenarios yet.
Great. Daniela, I have a question. So you mentioned there are certain neurons in the worm brain that encoded in them has the partial differential equation, which are more efficient in terms of encoding the knowledge. So can you elaborate on that? So if we consider this kind of differential equation as a more advanced form as compared to the step function, then what is the compression ratio in terms of compressing the knowledge from, hundreds of thousands to maybe a few hundred?
Well, so I don't have a theoretical answer that will guarantee what the compression ratio is. I can tell you that for driving, we have reduced for over 100,000 to 19, and so that's a huge compression ratio. I will tell you that if you look at the neural structure of C. elegans, that's the official name of the worm. This worm has 300 neurons, and the worm has a very good life on 300 neurons. It finds food, it moves in the world, it finds a mate, it passes time. And but it's interesting because biologists have very carefully specified what each of these neurons is doing from the point of view of the chemistry of the neuron. And it turns out that the neurons are specialized, so not all neurons are identical. There are motor neurons, there are sensory neurons. And so what we did was to take inspiration from those studies. I just want to be clear, we did not take the C. elegans neural structure, but we took inspiration in the idea that the neuron can do more than a step function, and that a neuron might be specialized. So we might have in robotics, we might have command neurons, we might have interconnection neurons, we might have motor neurons and sensory neurons. And these 4 types of neurons could then be composed in interesting ways to solve many mobility questions. We have looked at parking, we have looked at driving in the plane, we have looked at flight, we have looked at trajectory tracking. So a lot of activities that involve motion can be mapped onto neural circuit policies. We have a paper that appeared in October in Nature Machine Intelligence, and this paper describes the neural circuit policy model. And we've also described algorithms for how to synthesize such a circuit. So it's not so. In fact, we do have some recipes for creating these systems, but we actually don't have an analytical solution that will tell you exactly how much you will compress if you go from a regular to one of these new types of neurons just yet. But that's a wonderful question, and it's something that we should aspire to be able to answer in a theoretical way.
Okay. There's another question from David Smith.
So Alan Fern has been compressing large game-playing neural nets into relative small state machines. I'm wondering if there is any correlation between this more compact representation and the compact networks you're creating that use differential equations. So that's an excellent question. And I will say that there is a lot of, there are efforts on compressing neural networks. In my group, we have looked at other techniques to compress. And so, for instance, we have used the core set ideas used in computational geometry to prune the parameters. And we have shown that you could get rid of about 90% of the parameters without getting significant performance hits. So the performance hit is more, it's on the order of 5% on the error, on the bounds on the error. And so that's pretty awesome. There are a number of other efforts that are looking at how to take an existing network and compressing it. Our work with compression takes an existing network and compresses it. Neural circuit policies do not take an existing network to compress it. Neural circuit policies propose a different type of architecture. And this type of architecture involves having specialized neurons, like command neurons and sensory neurons. And there is a recipe, there is an algorithm for how to think about synthesizing this new type of architecture for a different kind of machine learning engine.
Excellent. So in the interest of time, we have to stop here. So let's thank Daniela once again for this wonderful talk. We learned so much. Thank you, Daniela.
Thank you very much. Thank you for joining us.
Thank you. So that's the end of the session, and we'll move on to the next. Thank you all.